My full name is Sophia E. My job title is Professor of Chemistry, and my place of work is Washington University in St. Louis in the United States. I'm a solid-state NMR spectroscopist, and my group focuses on three major areas at the moment. Of course, over the years, we've worked on different things, but right now it's optically pumped NMR. That's combining lasers with NMR together to do some new modes of hyperpolarization. We also do the computation of chemical shielding tensors and quadrupolar tensors, a sort of data analysis or machine learning type of exercise of crystalline materials. And then another area for us, I'm a material scientist, so we study materials for carbon capture and sequestration. So both the capturing agents that take CO2 out of the air, but also minerals, let's say, that can trap and store that CO2, carbon dioxide. Carbon dioxide capture, that is an incredibly exciting thing because of the opportunities to tune and tailor materials to take CO2 out of the air, for example, and then perhaps store it or process it in a way that allows us to remove the, let's say, the negative effects of these greenhouse gases. So materials synthesis teams and engineers are trying to understand how they can structure things in order to specifically pick out CO2 from the atmosphere and bind it tightly enough, but not so tightly because at some point you would like to release it. Maybe turning it into a feedstock chemical, or in the geosequestration area, the idea of sticking it underground and having it turn into a mineral, like a carbonate. So those processes are, by their very nature, for the most part, non-crystalline. So as I was mentioning before, amorphous systems, systems with dynamics, heterogeneous systems. In this case, NMR is perfect because it sometimes combines liquid, gas, and solid, even supercritical phases of matter. And in this case, NMR can see all of those phases, again, depending on conditions and how we set up the experiment. So we help inform synthesis teams. They're trying to find out where does CO2 bind, what are the conditions for it to be favorable, but also the recyclability of materials. Binding CO2, releasing it, and then binding again, and those cycles are important. So NMR provides a unique window. I think that NMR studies of materials generally are to make new materials for daily life. If you think about the iPhone that you might hold in your hand, that's composed of hundreds, if not thousands, of different materials, each of which has to be bound together and characterized. So ultimately, when we NMR spectroscopists can provide a window into better understanding those structures and how they're put together, that's a unique capability. And so we help designers and people who synthesize these special compounds in order to better tune their structures and their fabrication in order to make products for every day. Of course, in the CO2 capture area, if we can help these teams make better materials for being deployed in the field, of course, that would have immense benefits for climate change. But really, it crosses so many different areas. So it's not just limited to a couple of applications. It's really quite ubiquitous across a number of fields. Really, the things that are quite exciting in the field are the combination of NMR with some other kind of spectroscopy. These two things can come together in ways that we usually refer to as quantum mechanical. So hyperpolarization or dynamic nuclear polarization is an amazing demonstration of this. And I think even though DNP has been around for some time, we're now getting such a deep understanding that I think we will see more and more of these combination techniques come around. And so uniquely, there are phenomena that might be detected at the intersection of two forms of spectroscopy. So what we hope for in my group and others is that by combining two of these forms, we can look at things that one could not see, let's say, with just one modality alone. I was mentioning optically pumped NMR, and I can describe it really simply. Basically, you create an excited state with a laser, and then it's as if you're taking the NMR of that excited state. Now, that's an oversimplification. There's a lot more going on, but in essence, that excited state is not accessible normally by normal NMR. So it allows us to probe phenomena that exist in that excited state. And so I think that as groups like mine and others in the DNP world continue to expand, microwave and NMR and lasers and NMR, I think we're going to see an expansion of this area into new things that we haven't even imagined.